In this task, we will focus on explaining variational autoencoder models, also known by the acronym VAE. The VAE model uses a neural network to encode input data into a lower dimension representation. This representation is then decoded to generate new input data. To develop a condensed representation of the data, known as the latent space, a specific type of neural network is trained on a dataset. This latent space can then produce new data that is comparable to the original data. Here, we have an example of the architecture. We take some input data and use an encoder, as we did with the transformers, to reduce this data into a smaller representation, known as the latent space. Then, the latent space goes through a decoder that generates the output. The variation that allows for the generation of new results similar to the input data occurs when transitioning from the latent space to the decoder, moving from smaller to more comprehensive information. These models, like GAN models, are typically used in applications such as text, audio, and image production. They are especially effective in creating new content. However, they can also be applied to other tasks, such as anomaly detection and data compression. We have an example here where these VAE models have been used to generate new images from data. As we can see, they have generated images similar to the original one, but with variations. Now, let's explain this concept of latent space in VAEs better. The term latent is derived from the Latin word for to lie hidden. It refers to the process of simple dimensionality reduction while preserving the maximum information. We will use another example of dogs and cats to understand it better. We aim to reduce these images into points. Depending on the image size, there will be thousands of data points for each of these images. These points need to be reduced in such a way that they remain representative of the original images. In the latent space, similar images, represented by a series of points, should be close to each other. Here is an example with images of cats and dogs. If we convert these images into points, these points will need to condense the most representative information of these images so that the images of cats in the latent space are grouped together, and the images of dogs are also grouped together. Both categories should be easily distinguishable. This is what is aimed for when generating this latent space. How is this idea of latent space used in generating new images? Small manipulations in latent spaces lead to different images. The manipulation should be optimal enough to keep the data point closer to its equivalent and move away from other types. Here we have an example where this idea of latent space is used to generate new images. The input images are shown here, and we are attempting to generate new images based on these with subtle differences. For instance, we want these images to transition closer to the blonde hair class. These models add small variations to the original images to approach this blonde hair class. What if we want to add glasses? We can see how the obtained image is quite similar to the original, but glasses have been added in this case. The same goes if we want to transition these images to men. We can see how there are small variations. In this way, we can better understand how VAE models work, thanks to the concept of latent space.